All right, so I think we're up and running here. We got a full screen. So in this video, I'm just going to look at some of the problems that we've been working on, try to take a little deeper dive into them, ask some questions from geometric, numerical, graphical, and analytic perspectives, and just have a little fun, I hope. All right, so the first question is, can you approximate the sine of 3? And when I ask a question, just pause the video because otherwise, if I wait for you to answer, it's going to take an awful long time to get through this video. So you pause, I'll keep talking. Well, you have to know what this represents. You got to have a feeling for what the value 3 is. And that's what I found is the most difficult aspect of studying trigonometry is students gaining an understanding of what this number represents. And in this video, I'm hoping that on a number of the problems that I put on the board here, and there are a variety of topics, that you have a frame of reference. I made a picture frame. Okay, a little joke there. All right, so you need a frame of reference. So what's the frame of reference? Well, you got to know what a radian is. That's a radian. If it doesn't have a degree symbol, then I'm giving it to you as a radian. And it's much easier to model problems out there with radians. And radians come from walking around the circle. And if we make the circle a unit of 1, then you've walked around 6.28 units or 2 pi units, which matches up with 360 degrees. So that's a cram session. Now, to get at an approximate value, then I think it's helpful if you draw this side of the circle and get a frame of reference. Now, what's the frame of reference near 3? I'm hoping you're saying at this stage 3.14. And then where's the size of the circle? I don't know, maybe that's the center. And what do? We draw a triangle, drop the perpendicular, and measure the height, because the hypotenuse is 1. And I guess this is 3. Sure looks to me like that altitude is pretty much the same as the change in circumference length. So as I go around the circle, circumference length is getting larger. But if I were to draw the triangle here, the height is getting smaller. Sure seems to me that I just entered into a discussion about rates. The change in height, which is our y value, compared to the change in angle, which is now the x value, appears to be fairly similar. Right? If I have a circle, let me see if I can do this here without wasting too much time. So I make a circle, there's a circle, my whistle, right? What happens if I open it up? If I take some place, this is not easy to manipulate, some place on here, someplace, and I open up, I get the x-axis. So the x-axis is representing angles in trigonometry. And it matches up beautifully to counting numbers. 1, 2, 3. Well, 3 puts me here. What do you think the ratio is? Sure looks like the arc length isn't too hard to figure out, from 3 to 3.14, 0.14. And that's the change in radian. And the change in height is, well, let's find the height right now. It's pretty close to 0.14. It's almost 1 to 1, except that I said the rate of change, that's getting smaller, that's getting larger. Seems like it's almost a minus 1 to 1 ratio. Well, have you got a feeling for the sine function yet? 1 period from 0, that's 6.28 over here. That's the period. Circumference length, radian, 3 is about here. And if I zoomed in on that, it kind of looks linear. If I do a good enough picture in a proper scale, 1 to 1, then does it seem plausible that I'm going down at 1 to 1? Well, how about the heights? How are the heights changing here at 90 degrees? They're not. The heights are staying near 1. All right, so there's very little change up here. It's more like a 0 to some kind of distance change on the radian. So I don't care what you put here. Doesn't matter. Maybe that's what, 1.5? I know that's 1.57, that's half a pi. Maybe over here I got 1.6. Okay, so things change by 0.8. Does it matter how things change here? That's not changing, no. All right, so it's important to dive a little deeper with each of the things that we're studying. So it's not an example of do this, get that. All right, so we'll be doing some other plenty do this, get that. But we want to know why we're doing this to get that. All right, so we'll have a series of questions here. X squared plus 6x plus 11. Okay, I know you know how to graph it. I know you can evaluate it. Some of you can find roots quickly, so on and so forth. But I'm going to ask the question, can you show me the geometric manipulation, commonly referred to as completing the square? Can you work with the geometric shapes that explain, underlie all of the mechanics that we're doing? Okay, so you pause the video and think about that. I'm just going to do it. The topic is quadratics. Why? Because the first two terms form a quadratic. And that quadratic happens to be x times x plus 6. And if I do that and add 11, I have a calculation that measures area and gives it a little adjustment. Well, I can take that and take the longer side, make it shorter, tack it onto the other side to make a square. And that's why we do x plus 3 times x plus 3. Because it gets us the first two terms, x squared plus 6x. We get those same two terms here, but unfortunately we get another 9 units, which is not the same area as this. But if I subtract 9, it's now the same calculation, provided I remember to also add 11. That's what underlies a lot of what we've been working with. And don't get me started on quadratics, we'll talk too long. Okay, here's another situation. We're at the end of the term. Have you done that enough to know how to do it? So pause the video. Okay, but what I'm asking you to do, I shouldn't pause it yet because I haven't formally asked the question, is can you tell me the center and the radius in 10 seconds or less? All right, so you think about it for a second. Could you, so mental math this thing now, and then I'll turn around and I'll try to do it in 10 seconds or less. And I haven't looked, I just randomly put some numbers up there. All right, so I'm going to look. You pause the video. I'm going to just see if I come in under 10 seconds. I don't know. I felt slow. I felt slow just then, but let's find out. Completing the square, well, from the last picture over here, what did I do? I took the number 6 and I cut it in half. So I'm looking at minus 10 and I'm cutting in half. And if I do, I know I've got x minus 5. Hence, that's what makes a 0. Y plus 3 makes a 0. Adding, squaring, minus 25. Plus minus 9 equals 43. Let's see if I added this up right. 34 and 43, 77. Yes. And that's the square root. So therefore, Pythagoras says this morphs into positive square root of 77. And we're squaring them. There's your Pythagorean relationship. There's your Pythagorean relationship, and we have a new axis, 5 units less, 3 units longer. So I'm down here at 5, -3, with new units, new axes. That's the x minus 5 length, and this is the y plus 3 axis. And I'm drawing triangles. Square root of 74 is near 9, right? Square root of 64, 8. Square root of 81, 9. I'm about 8.5 units. So 8.5 units maybe takes me out to there. There's a triangle, A for instance, and I'm drawing the circle around it, so on and so forth. Not too bad for rotator cuff problems. Let's keep going. Another 10-second question. If you know how to do perpendicular to 5x plus 3y equals 80 through the point, in, out, then I'm wondering if you can write your answer. Okay, just write it. Not even think. Yeah, just go over here and go, oh, 3/5, x minus in plus out. I didn't do any thinking. Why? Because I put my answer next to the original problem, and it sure looks like all I did was look at that, and go ahead and do it, providing you understand the mechanics behind it and the concepts behind it. Slope of a line is the interplay of inputs and outputs. It has nothing to do with the constant. So therefore, how would I get y alone? Well, first off, 3y is equal to negative 5x, and therefore y is equal to minus 5/3 x. And if I go over 1 and up 2, that's a slope of a line. Perpendicular is over 2 and down 1. Original slope 1/2, perpendicular negative 1/2. So you see the negative reciprocal. All right. So here's the original slope. There's the negative reciprocal, which is buried in the problem. I suggest you do that when you even do calculus. You'll be hitting these differential equations, dy dx equals 2x, y minus 4, and let's say a 0 gets you 20. I want you to be able to look at your answers and say, oh, yeah, this is 16 e to the x cubed over 2. Oh, is that right? 2/3, excuse me. Been a while since I did that. Plus 4. Yeah, that's the function that produces that rate of change. You have no idea why I just did that if you're just in Algebra 2, but it's something you can do. And I haven't done that in 10 years, so I hope I didn't make a mistake. All right, the sign of. Oh, I'm going to give you one. And here's another chance to talk about frame of reference. All right, this is frame of reference moment. So let me make up a problem, and let's see if you can answer it in 10 seconds or less. Ideally, 5 seconds or less. 11 pi over 3. Go ahead, pause the video, try it. No, I don't have to wait. So in my mind's eye, I think I'm going to get minus root 3 over 2. Let's check it. What's my frame of reference? 12 pi over 3, which happens to be twice around. Okay, and I want to be at 11 pi over 3. There's a good drawing. And I want this height. Okay, I see the 30, 60, 90 triangle. I see the negative pi over 3 radius change from there to there. Okay, that's minus 1, approximately minus 1.05, I think, divided by 3. I'm sorry, minus 1.05. All right, 3 into minus 3.14. Yeah, close enough. That's a nice approximation. A little bit more than 1 radius length. All right, and well, yeah, that is that. And I've asked you to memorize what root 3 over 2 is, and I still am not hearing quick answers. Negative 0.87. This is negative 1, another frame of reference. Okay, so that height, yeah, it's a little higher up on the circumference. Makes sense to me. All right, here's another. You're doing these problems, you might as well be able to answer the roots in 3 seconds or less. Just write your answer, not have to think. But you need a frame of reference. All right, what's your frame of reference? Well, it's an X answer. I hope your frame of reference is an X value. There's only one X value on the board, it's 5. And I know to get to 0, I'm going to have to actually flip it in the other direction in order to get to 0. So what do I know? I know I've got inverse operations, and I know I have imaginary answers. So what are the inverse operations? Well, what's the inverse of multiplication? Division. What's the inverse of getting from 7 to 0? What's the inverse of plus 7 if I got to get to 0? Well, it's plus minus here, right? I guess all I'm saying is you got to move 7 units. I'm just looking at it and telling you what the roots are. And we'll put it in here in a second, but I think in graphing form, 3 is the multiplier. x minus 5, I'll put that there, x minus 5 gets squared plus 7 equals 0. So what would you do if you're solving this? Well, I think you take away 7, gone. I think you're dividing by 3. It's gone. I think you're taking a plus minus square root. And I know that a negative means it's imaginary, 7/3. That's gone. And now we've got to add 5. Well, let's put our answer in and see it work. I'm a big fan of repetition. This has been done numerous times. That's all the way, and I. Well, the first thing I see is the 5s go. Then I square a plus minus, I just get a positive. I square what's inside. Well, that takes care of that. And if I square that, that becomes that. So I've done the squaring. I know I squared is -1, so that changes that sign. I know 3 divided by 3 cancels. I don't have to do that out. And I get -7 plus 7. And I move on. So I think if you got a vertex in the A value, it's nice to know the roots. Of course, I didn't mean that. I wanted actually to equal 90. I really was hoping to get this to equal 90. So maybe you can pause the video and get that answer. And I'll just keep working. Hope the numbers speak for themselves. If not, be a mathematician and look at why I wrote that. All right, so 1 is approximately, well, 1 is 1, but what is it in terms of degrees if this is a radian measurement? How would you get it? How would you get that number? I guess I got to look at this. Well, I think that 180 degrees matches up with pi. So why don't I write it this way? 180 degrees in a different language is pi. And that's 3.14, but I want 1. I just want 1 radian. And I want to know what it is in degrees. Well, I guess I got to divide by 3.14. And if you do, you get about 57.3 degrees. I think it's important to know what 1 radian is approximately in degrees, because I think if you're going to understand calculations, you got to be able to work with numbers and see how they work. Otherwise, you're memorizing, do this, get that. And that's unfortunately what happens most of the time. Okay? So it's important to kind of get inside calculations and play with the numbers. And we'll do that over here. It's not something we haven't been talking about. And I'm not a big fan of lines of demarcation. I've had Algebra 1 students who, in half a semester, get to work with calculus because they just dive into it. And each day make progress. And, you know, we're doing derivatives and integrals after a month. And that's students coming out of COVID and, you know, wondering what the graph of y equals 2x looks like. So it's doable, but you have to be willing to dive in. All right, so the mechanics of writing equations to tangent lines to quadratics is about the easiest thing we could do with a day or two of practice. Do this, get that moment. And I'm happy to start there because mechanics are important. And so we'll do a few of these, do this, do that. We'll do 3 of them in a row very quickly. But based on the conversations we've had in class, I'm going to ask a few questions here to try to get into a deeper understanding of rates of change. And how we use rates of change will be something I talk a lot about in the next 3 weeks. All right, so I saved some time. So the equation of the tangent line at y equals 6. I'm trusting that people know to plug in 6 to get 49. And then you can write x minus 6 plus 49. So let's make sure I did it. 72 minus 30, 42 plus 7. Yeah, okay, double checked. Now, how do we get the rate of change at 6? How do we do it for x squared? Yeah, I've been putting those tables in front of you. Can anybody square? Well, I'm answering my own question, so pause the video. How do we get the rate of change? Well, at the Algebra 1 level, we put a another number in that gets us y2 minus y1 over x2 minus x1. Now, if they picked 100, we'd get an average rate of change, which wouldn't reflect the tangent. So I'm going to pick a number like 6.00001. And I've been squaring that number in front of you. I've handed out a table of values. And if you want to really get an understanding, you actually have to look at the table of values and see the patterns for yourself. So I guess I'm pausing the video and I'm saying, has anybody done that work enough to know what that is? Okay, I'll just write it. It's 36. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's what it is. And if we want to estimate the change, well, I don't think there's change from 36 to 36. I think the change from 6 to 6.01, I think that's the change, and I think that's the change. So if I put 0.00012, and I ignore that because it's so small, that number right there is really 0.000001234 That's what I just erased. Now, how is that going to affect the calculation over here, this division? This division of y2 minus y1 over x2 minus x1. And you say, well, why is he telling us this? Because we're looking at y2 minus y1 over x2 minus x1, which is an algebra 1 concept. Except that we're doing it over a small distance. And I'm planting some seeds. And I don't think that seed is something you can't understand. So I'm actually changing at 6. I'm changing at 12 to 1. I see that change right here. I see that change, 12 to 1 at x equals 6. But I'm doing what to it? I'm doubling it, which means I'm changing at 24 to 1 from this term. And how do linear functions change? They change at a constant rate. That is another algebra 1 discussion. I'm not going to take the time to look at what happens. 6 gets me minus 30. What does 6.001 get me? Okay, not going to do it. I'm not going to show you 30.000 something like that. Oh, I guess I just did show it. The question is, did I do a good y2 minus y1? I don't know. But it changes at a constant rate. It's going down at 5 to 1. All right, so looks like I got the slope. 24 minus 5 is 19. And I answered the question. Now let's backtrack a little bit. What did I find here? That there's a formula for x squared. This is what we've been looking at in class, 2x. In other words, if I picked another x value, 3 gets me 9. Can you do 3.001 and tell me what I get? Well, check it out on a calculator. I have. That's what you get. And it sure looks like I'm changing at 6 to 1. So in essence, I can get what we call a formula for how this function is actually changing. And it's based on change in y over change in x. And I don't know change in y, but I can tell you what the change in x is. It's I'm just doing a small change and looking at the patterns. And what was it? What was that small change? It really was, let's erase, 2x times 2. In other words, I can just take the 2 and double it, and that's the rate of change of that quadratic. What would the rate of change of this quadratic be? I hope you say 6x. What would the rate of change of this quadratic be? I hope you say minus 10x. So now when you look at a function, you not only know how, where the vertex is, where the y-intercept is, but you also know how things are changing. It's important to know how things are changing when you want to make policy decisions on things like how many people are getting sick from COVID, what's the transmission rate. Those are important discussions, and the math behind them determines, well, sometimes science determines policy, sometimes not. We're in a whole different world right now. Right? But basically, you're hoping that you're using science, to study problems, things that we know are true. So let's give you an example of one. Let's have you try now. Let's look at this a little deeper. So what does this graph look like? Let's take a look at that graph, and that's what we did in class yesterday. So pause the video and take a look at it. Tell me what you think that graph looks like. I'm going to keep going. Back to a frame of reference. I'm going to use -3 as my frame of reference. Right there, -3. That's, of course, when I put a 0 in, yes? 0 gets me -3. Okay, what am I doing there? I'm going up at 8 to 1. That's what we practiced yesterday in class. So I'm going up at 8 to 1, which means I actually have the equation of the line tangent. Oh, yes, there it is, 8x minus 3. Yes, this is slope of 8, x minus 0 plus 3. I think that can be written as 8x plus 3, and I think that's a positive number. Oh, I guess the tangent was there all along. What kind of shape do we have? Cup shape up. If I'm increasing, I think cup shape up's got to go that way. And what do I have? 4 minus b over 2a, that's fine. Minus b over 2a, minus 8 over 8, -1. Well, that makes sense. That's to the left of that. And if I put -1 in, you take your time to do it, I'm going to get -7, which means I have the roots now. We'll come back to the roots, give you a chance to remember what we did a few minutes ago. But now I want to get, sometimes instead of writing dy or dx, we just capital to smaller letter. Tells me how this is changing. Can you tell me how it's changing? Can you double that? Drop it down 1 and add the constant rate of change. That's not changing. All right. Can you set that to 0? Oh, yes, slope of 0 at -1. Can you put a 0 in? Oh, slope of 8. Okay. Well, how about at negative, well, I guess I got to go bigger. How about at +1? Well, you got to find out what the area is at +1. 12 minus 3 is 9. So I guess I've got x minus 1 plus 9. Can you tell me the slope at that instant? Oh, yeah. I got something that tells me that. I'm going up at 16 to 1. Wow. I was going up at 8 to 1. I thought I was supposed to go up by just 2 units. Yeah. I thought that's what happened for x squared. You go up by 2 units. Oh, yeah, I multiplied by 4. Oh, yeah, my slope did go up by 8 units. Yeah. I think you need to see this, and I think you need to see it well before you get to studying limits and derivatives and integrals. And I'm not going to push it more than maybe the cubic. If you take to this, then I'll show you the rate of change of the cubic. It's not hard because I can draw the pictures. I can draw the picture of how a 6 by 6 is changing at 0.001. And if I want to maintain the dimensions being equal, then if I give a height of 0.001, I need a width of 0.001. And I can't show that distance. It's just a little dot. But I can diagram it. And I can show you that that was your 0.000 because I'm squaring that. And that's really small at the cusp. So my accumulation of area is a strip of area there and a strip of area there, and that strip has that width and it has this height. I think that's 0.006. I think that's 0.006, and I think I have 2 of them, which make 0.0012. Well, I did that poorly. 0.012. Yeah, there, I can add now. That's good. Otherwise, I got to go back and practice my 3rd and 4th grade addition of decimals. And I think my dimension changed by 0.001. There's another geometric analysis of finding slope of a quadratic. And I think people understand square area and new square area when you add a little layer of change. But don't think that has to wait until your senior year. Nor do I think it should. Because if we're going to change how your brain works and connect neurons, then we have to have deeper discussions than just do this, get that. Good luck with that. So explain this calculation to me. Pause the video. Tell me what I should be looking for when I write that. Tell me what should be in here in that parentheses so I can answer the question quickly. All right, so log base b means b to the what? So I think I want to write something here as b to the what? And then my answer is, who's buried in Grant's tomb? What? Now, what is this what? It's a value of an exponent. So this LOG is asking you to find the value of an exponent on top of b. Wouldn't it be nice if you wrote this b to the what? Because then you'd have what? So let's try one. Let's try log base 2 of 2 to the 5 over 2 to the 3. I'll put a bracket here, all to the negative 4. And let's see if you can answer that. Well, pause the video. I'm just going to keep going. I think that becomes log base 2 of 2 squared raised to the what? Negative 4. And I think that can be written as 2 to the negative 8. I think I'm ready to tell you what is. So I think if you understand what you're looking at, if you understand how to ride a bike, you can ride a bike. Of course, when you first got on it, you had to fall down a few times. But you got back up and you practiced, and then you can ride a bike. That's no different. So now let's change it to ln and answer the question. ln, well, I got to erase that. And let's do an approximation. Let's see if we can get to an approximation. Okay, you pause the video. Well, it's actually a little more complicated, right? I mean, I could do it in terms of 2 and then change it. And that would be a shortcut, I think. But let's not take a shortcut. Let's talk about 2 being e to the 0.7 approximately. And 2 here, e to the 0.7. Negative 4, I don't have to change. So I have to do all this work. I think I have to do 5 times 0.7, which is 5 times the ln of 2. And I think I have to subtract 3 times the ln of 2. And then I think I have to multiply that by negative 4. Well, I think 5 minus 3 ln of 2 is 2 ln of 2. And I think I'm multiplying that by negative 4. So I think I can get it down to minus 8 ln of 2, but 2 in e notation now. I got to do e notation. I didn't do e notation. Well, I kind of did, because ln is e notation. All right, so 8 ln of 2, which is approximately ln of 2.7. 0.7, excuse me, 0.7 times negative 8, negative 0.56, I think, as just playing with the numbers. All right, so what do we have up here? We have, well, that's the rules of logarithms there, by using the rules of logarithms. Is there some way that I can make this more accessible to what we're doing here? I don't think so. I think I asked the question a little harder than I would have liked to have asked. So let me ask this one. All right, just see if you can polish this off in 5 seconds or less. Let's look at e to the 3, e to the 4, and let's say that that is raised to the negative 3, and you give me your answer. Hope you said minus 21. All right, what's another name for e to the 3, e to the 4? You add there, you add e to the 7, and then that times that gets us minus 21. And you need to know that ln is base e, which we don't write. There's your answer. Okay, so maybe that moved the needle a little bit. Now, just a couple more questions. These are the things I'm going to be asking in class today. In this video is there, so you don't have to take any notes. These are the questions I'll be talking with you about in class. All right, I think I already did this one. Let's do period. Period of the function. We had this conversation. We don't have to have that. I ended up talking about it over there. All right, so what's the period of this function? Well, let's get the period of y equals sine x first. Sine x, okay, and that's a circle. And if you open up a circle, we make a little cut there and unwind it, you get the x-axis. What's on there? 1.57. What happens to heights in the first 1.57 radians? We go up to a height of 1. Okay, so we start at 0, height of 1, 3.14, back to 0, 4.71, 4.71 radius lengths takes us to -1, and then we come back 6.28 radius lengths later, back to 0. So how far is it from 0 to end of one revolution? 6.28 units, but we don't say 6.28, we say 2 pi. All right, so the normal period starts at 0 and ends at 2 pi. And we want our parentheses, which is all about the angles, to equal 0. And we want it to equal 2 pi. I think I know my new period. I think my new period goes from 0 to 8 pi. All right, so I'm starting at 0, 8 pi units later, which really is 4 times what I drew before. Oh, 4 times. Oh, yes. Division became multiplication. Ah, God, that would be a nice way. So I'm multiplying x by 1/4, and if I take that multiplier and divide it into 2 pi, oh, that's a quick way for getting that period, providing I know where I'm starting. Now, if this was starting at 5, then my 5 plus 8 pi, I would be starting at 5 and ending at 5 plus 8 pi. Now, I think you need to hear these things. All right, and what's the shape of the sine function? Well, you go around the circle, you go up, you come back down, you go down further, and you come back up. You go up, you come back down, you go down back, and you, oops, I wanted to hit that. Well, I did hit that. Everybody saw me hit 8 pi right there. No, that's exactly what I did. Perfectly done. Yes, perfect, perfect. So now the question is, what used to be a height of 1, what used to be a height of 0, and what used to be a height of -1 is being changed. First off, this kicks out numbers between plus and -1. I think I'm now going up 5 and down 5. It sure looks like my midline isn't 0 anymore. I'm measuring from 7. That's a frame of reference. Yeah, so I got all kinds of numbers that I can find now. 8 pi gets me 7. That means 4 pi gets me 7. And that means 2 pi gets me 5 plus 7, 12. 5 minus 7, 2. So there's my range, 2 to 12. And 2 pi, let's plug 2 pi in. 2 pi divided by 4. Oh, pi over 2. Pi over 2. Oh, where's pi over 2 on the circle? Straight up. That's 1.57 radius lengths. So if that's a radius, then I got 1, and a little bit more than half of that takes me to there. 1 radian, 57.3 degrees. Well, what's half of 57? It's near, 20, 24. You had 24, you're pretty close to 90 degrees. Getting a feel for the numbers. That's what we're after, trying to get a feel for the numbers. Okay. So do I have any more questions? No, we'll send you to the board and I'll pick your brain. All right. Hopefully you had a variety of considerations to consider. Toodaloo.